We built a $10 billion time machine to see the beginning of the universe. But the greatest test of this incredible power wasn't a signal from 13 billion light-years away, but a whisper from just 120 light-years distant. When the James Webb Space Telescope locked onto the planet K2-18b, it detected an impossible signal. This signal was fainter than 1/10,000th of the star's light. Yet, within it was the molecule dimethyl sulfide, a potential sign of the life. Its atmosphere should have contained ammonia, but it didn't. Evidence of an active system. But here's the real paradox. Even our most powerful telescope is working at its absolute limits to confirm this life-changing data. If you're excited by this hunt, pushing the boundaries of technology, subscribe. Because the evidence you're about to see teeters on the very edge of belief. We begin now. For years, our search for a habitable world was locked onto a single model, a copy of Earth. We looked for a rocky surface. We looked for a thin nitrogen-oxygen atmosphere. We looked for that perfect distance orbiting a star like our Sun, where liquid water could exist on the surface, because that was the only formula for life we knew. So, we designed our missions around this framework and interpreted the data through this lens. But this approach was also limiting. It ignored countless worlds where life might exist, in forms we could not even imagine. It left us blind to a vast portion of the universe. Then, the James Webb Space Telescope looked at one of those worlds, K2-18b, and everything changed. Because Webb didn't just show us a new planet. It showed us an entirely new possibility. To understand this new possibility, you first need to know the planet itself. Its name is K2-18b. It belongs to a category of planet that has no equivalent in our solar system. Astronomers call them sub-Neptunes, because these worlds are larger than Earth, but smaller than Neptune. In our system, there's a sharp divide between small rocky planets and giant gas and ice planets. But when we looked at other star systems, we saw that this gap wasn't universal. In fact, sub-Neptunes seem to be the most common type of planet in the galaxy. They are everywhere, and yet we had no local example to study up close. That is why K2-18b is so important. Its mass is about 8.5 times that of Earth. Its radius is roughly 2.5 times larger than our planet. These numbers make it a definitive sub-Neptune, but they don't tell us what the planet is actually like. But the truly staggering thing is its distance. Right now, it sits about 120 light-years away from you. This is an impossible distance on a human scale, because our fastest spacecraft, travelling at about 17 kilometers per second, would take more than 2 million years to cross it. Yet, on the scale of the Milky Way galaxy, which is 100,000 light-years wide, this planet is practically our next-door neighbour. It lives in our neighbourhood. And that is why the light from its atmosphere is close enough to reach the mirrors of a telescope orbiting our own Sun. For years, it was just a line in a database, until Webb looked its way. So what kind of world could this planet be? This question led scientists to a brand new concept, one they called Hycean world. The word Hycean is a combination of the words hydrogen and ocean. A Hycean world is a planet with a thick hydrogen-rich atmosphere, sitting above a global liquid water ocean. But this isn't like any ocean you know. It could be hundreds of kilometers deep. That's far deeper than the deepest point in Earth's oceans, which is about 11 kilometers. The hydrogen atmosphere above it acts as a kind of insulating blanket. It traps heat from the star, keeping the surface warm enough for water to remain liquid. This idea was revolutionary in the search for habitable worlds. Because it suggested that a planet like K2-18b might not need to be rocky like Earth to support life-friendly conditions. Instead, it could be a water world, where biology emerges and thrives in a vast ocean, under a hydrogen sky. This hypothesis opened a door. It showed that the most common type of planet in the galaxy, the sub-Neptune, could in some cases be a world with a liquid water ocean. This is why K2-18b drew so much attention. It wasn't just a potentially habitable world. It was a potentially habitable world whose atmosphere could actually be characterized by today's instruments. Understanding how that characterization is done is the key to everything. The technique is called transit spectroscopy. You might wonder how it's possible to read a planet's atmosphere from so far away. Think of it like this. As K218b passes in front of its star as seen from Earth, a tiny slice of starlight filters through the outer edge of the planet's atmosphere before continuing on its way to us. This sliver of light is extraordinarily faint. It represents less than 1/10,000th of the star's total brightness. But within that faint sliver, molecules in the planet's atmosphere leave their mark. Each type of molecule absorbs light at specific wavelengths, just like a fingerprint pressed into a spectrum. Water vapor absorbs certain wavelengths, methane absorbs others, carbon dioxide leaves its own distinct pattern. So, by carefully measuring which wavelengths of light are slightly dimmed during a transit, astronomers can determine which gases are present in the planet's atmosphere. This measurement is not simple. Yes, because gas the star K2-18 is billions of times brighter than the thin ring of atmosphere around the planet. Extracting a useful signal from this imbalance is like trying to detect the color of a soap bubble floating in front of a searchlight from the other side of a city. It requires extraordinary precision and long observation times. Webb was designed for exactly this kind of work. Yet, even the K2-18b observations pushed the telescope close to the limits of its capabilities. The first results came in the form of a spectrum, a graph showing how much light was absorbed at each wavelength as the planet passed in front of its star. And on that spectrum, certain features stood out clearly. There was a strong absorption signature from methane, there was another from carbon dioxide, and along with them, there was a much fainter, more tentative signal. This signal matched the absorption pattern of a molecule called dimethyl sulfide. This molecule is at the very heart of the question this journey is built upon. But before we get there, it's worth spending a little more time with the planet itself, because these observations showed us not just the presence of a few molecules, but that this world could be far more complex and far more interesting than we ever predicted. What Webb found was not just the chemical inventory of an atmosphere, it was the whisper of an ocean, and perhaps of something moving within that ocean. That is why every dip, every absorption line in that faint spectrum carried the secrets of a world 120 light-years away. And as scientists began to decipher those secrets, they realized that what they found could have implications deeper than anyone could have guessed. Because that data pointed to a chemical imbalance, it suggested the atmosphere was not being left to itself. Something was constantly disrupting that chemical equilibrium, and that whisper showed the planet's atmosphere was not in a state of chemical equilibrium. This is the steady state a mixture of gases reaches after all possible reactions have taken place. Because, in equilibrium, the amount of each gas is determined solely by temperature and pressure. No outside intervention is needed. If K2-18b's atmosphere were just a bag of hydrogen, carbon, nitrogen and oxygen, left to its own devices to reach equilibrium at the planet's temperature, there should be ammonia. But Webb found no trace of it. This is why this situation was incredibly important. The absence of ammonia suggests that something is preventing the atmosphere from reaching equilibrium. Something is removing the ammonia or preventing it from forming in the first place. This should remind you of something. Because, here on Earth, the atmosphere is also far from chemical equilibrium. We have both oxygen and methane in our air. These two gases should react with each other and disappear over a few million years. But there's a reason they coexist. Because living organisms are constantly replenishing them both. Plants produce oxygen. Bacteria in the digestive systems of animals produce methane. Without life, Earth's atmosphere would settle into a very different and much more boring air equilibrium. So, when scientists saw that K2-18b's atmosphere was also out of balance, it raised a mind-boggling possibility. Maybe something on K2-18b was actively maintaining this disequilibrium. This is not proof of life, because non-biological processes could also potentially explain these observations. But this was the kind of atmospheric signature that scientists had long identified as a possible indicator of biological activity. And then there was that other molecule, that most tantalizing whisper, dimethyl sulfide. It's a small molecule made of two carbon atoms, 6 hydrogen atoms, and 1 sulfur atom. It's called DMS for short. On Earth, it is produced almost exclusively by microorganisms in the sea, specifically oceanic phytoplankton. These tiny organisms produce dimethyl sulfide as a byproduct of their metabolism, and this gas is released into the atmosphere in vast quantities. In fact, it's one of the most abundant sulfur-containing gases in Earth's atmosphere. If you've ever walked along a beach and noticed that slightly sharp, almost cabbage-like smell carried on the sea breeze, you have smelled dimethyl sulfide. It is the smell of ocean biology at work. Because, on our planet, there are no known non-biological processes that produce dimethyl sulfide in significant amounts. Methane can come from volcanic activity, oxygen from the breakdown of water. But dimethyl sulfide, on Earth, has no established abiotic or non-living source. It is, as far as we know, solely a product of life. That is why, if it were definitively detected in the atmosphere of another world, it would be extremely difficult to explain without invoking biology. This is why the possible detection on K218b sent a shockwave through the scientific community. Because this wasn't just a molecule, it could be the herald of a revolution. To better understand this planet's environment, we must look to its star. K218 is a red dwarf. This is a type of star that is smaller, cooler, and dimmer than our Sun. Red dwarfs are the most common type of star in the Milky Way galaxy. Estimates suggest they make up roughly 70 to 75% of all stars. They are so dim that not a single one is visible from Earth with the naked eye. So while they are invisible to us, they are the most populous residents of the universe. Their surface temperatures are about half that of our Sun, around 5,000 degrees Fahrenheit instead of 10,000. This means their planet's habitable zones must be much closer to the star. K218b orbits its star at a distance of about 14 million miles. While Earth is 93 million miles from the Sun, this close orbit means the planet is likely tidally locked, meaning one face is permanently turned toward the star while the other is in constant darkness. But the most important feature of these stars is their patience. While our Sun has a lifespan of about 10 billion years, the lifespans of red dwarfs are measured in trillions of years. This means that K2-18b, just if it has conditions conducive to life, has had an almost unimaginably long time for life to emerge and evolve. It took about 1 billion years for the first simple cells to appear on Earth. This planet could have had 10 or even 100 times longer. So, we've assembled all these conceptual pieces, and now we have a sub-Neptune, one of the most common types of planets in the galaxy. This planet presents a new, potentially habitable model we call a Hycean world. Its atmosphere shows a chemical disequilibrium that could be a sign of the life, and most importantly, it carries tentative traces of a molecule, dimethyl sulfide, that on Earth is produced only by life. All of this is happening in orbit of a patient red dwarf that will live for trillions of years. We're no longer just speculating. We're no longer just asking what if. We can now measure. We can now wonder. With this theoretical framework in hand, it's time to return to the central question. What exactly did the sensitive instruments of the James Webb Space Telescope see in that faint, ancient light from 120 light-years away? What were the actual findings? What were the actual findings? This is where the real shock comes. Because when Webb collected that faint light from 120 light-years away, the data it obtained was beyond theoretical models. It wasn't just a whisper, it was almost a scream. It was a clear portrait of unexpected molecules, imbalances that shouldn't be there, and a possibility that seemed impossible. Get ready, because now we dive into the real findings. The first finding came as a pair, methane and carbon dioxide. Both were in the spectrum, and very clearly so. Their presence alone was not a surprise, because just theoretical models had predicted that sub-Neptune atmospheres like K2-18b's could contain these gases. But the real shock was their coexistence. It was like a lion and a gazelle living peacefully in the same cage. Chemically, it shouldn't happen. Because in a hydrogen-rich atmosphere like K2-18b's, carbon dioxide should be chemically converted into methane and water. If the atmosphere were left to its own devices, the carbon dioxide should have disappeared over time. But it was there, with a strong signal. This indicated that something was constantly replenishing it, or that the gas was interacting with a reservoir that prevented its complete conversion. A natural explanation was a massive liquid water ocean. If K2-18b truly has an ocean hundreds of kilometers deep under the gravity created by its 8.5 Earth masses, this ocean could dissolve carbon dioxide from the atmosphere, but also release it again through chemical processes, just like Earth's oceans regulate our planet's climate. And so, the coexistence of these two gases was the first strong piece of evidence supporting the Hycean hypothesis, the idea that the planet is an ocean world. But this was just the first piece of the puzzle, because the real anomaly was hidden in something that wasn't there, and that anomaly was like a ghost, a molecule that should have been there but wasn't. Ammonia. When scientists looked at the spectrum, they had looked for it. Because, according to the rules of chemical equilibrium, in a hydrogen-rich atmosphere with a temperature in the range of 80 to 120 degrees Fahrenheit, like K2-18b's, ammonia should have been present in detectable amounts. It wasn't a possibility, it was a requirement of basic chemistry. But there was no trace of ammonia in the spectrum, zero. This was incredibly significant. It was the most definitive proof that the atmosphere was not in equilibrium, because the absence of ammonia indicated that something was actively destroying it or preventing its formation. This situation drew a direct parallel with Earth's atmosphere. The coexistence of gases that should react with each other, like oxygen and methane in our air, is proof that life is constantly engaged in chemical production. The absence of ammonia on K2-18b implied something similar. Perhaps a process was consuming ammonia and producing methane. Just as biological processes on Earth consume carbon dioxide and produce oxygen. This discovery shook the scientific world, because this was no longer just a possibility. This was measurable proof that the atmosphere of a world 120 light-years away was defying the known rules of chemistry. It was an anomaly, and anomalies are the harbingers of great discoveries. But the real bombshell was saved for last. The faintest signal, the most unbelievable possibility, that hesitant trace that appeared just above the noise level of the spectrum. When scientists analysed this signal, they saw that it matched the absorption pattern of a molecule called dimethyl sulfide. 2 carbon, just 6 hydrogen, 1 sulfur atom. On Earth, this molecule has only one major source: life, specifically phytoplankton in the oceans. On Earth, volcanoes, geological processes, or any known non-living chemical reaction do not produce this molecule in significant quantities. It is the signature of biology. It is the breath of the ocean. And now, a ghost of that signature had appeared in the spectrum of a Hycean world 120 light-years away. Yeah, this detection itself was the moment science fiction became reality. But the scientists were cautious. The research team described it as a possible detection, not a confirmed finding, because the signal was very weak. It was on the edge of what the instrument could reliably measure. It appeared at wavelengths where other molecules could also produce similar absorption features. So, it was difficult to be sure whether the signal was truly from dimethyl sulfide or from something else. They did not claim to have found proof. They said they found a clue, a tantalizing suggestion, and that more data was needed. But even that clue was enough. A clue that would change our view of the universe forever. Because that weak signal, that tentative detection, raised the deepest question in human history. Were we hearing the breath of another world? When all these findings came together, the picture that emerged was mind-boggling. A pair of gases that shouldn't be together, a molecule that should be there but was missing, and the ghostly trace of a molecule that should only be produced by life. But how do we explain all these pieces? What lies behind this strange chemical cocktail? Because that dimethyl sulfide signal itself, that ghost whisper, could only be heard by an impossible technology. The real shock behind these discoveries is not just the findings themselves, but the engineering marvel that allowed us to see them. Because the James Webb Space Telescope itself is a discovery in its own right, a technology that pushes the limits of what humanity can do. Sobus, now, we look at the facts behind that impossibility. The first shock was the telescope itself. Its very existence is a miracle. This isn't just a telescope. This is the product of a nearly 30-year development process. thousands of engineers and scientists from more than a dozen countries, and a cost of roughly $10 billion. And it wasn't sent into Earth's orbit, because that was too hot and noisy. Instead, it was sent to a point about 1.5 million kilometers from Earth, known as the second Lagrange point, coexist, or L2. This is a special place. Because, here, the gravitational pull of the Sun and Earth allows a spacecraft to orbit the Sun at the same speed as Earth. This was critical because the telescope needed to stay extremely cold. Its infrared detectors are so sensitive that even the faint heat from the telescope's own structure could overwhelm the signals from distant stars. To prevent this, Webb carries a sunshield the size of a tennis court, made of 5 thin layers. Thanks to this shield, the temperature on the shaded side drops to about minus 223 degrees Celsius, minus 370 Fahrenheit. The instruments operate in a permanent deep freeze, but the real impossibility was its massive 6.5 meter mirror. This mirror was too large to fit in one piece inside any rocket's nose cone. So, it was designed to be foldable. After launch, over a 2-week period, the mirror unfolded piece by piece. Each of its 18 hexagonal segments was aligned to within fractions of a wavelength of light. The precision of this alignment is unbelievable. The parts had to be positioned with an accuracy of about 1/10,000th the thickness of a human hair. If even a single segment had failed to deploy correctly, the $10 billion mission would have failed. But every segment worked perfectly. The impossible was achieved. But there was another shock. This was the star the telescope was looking at. K2-18, a red dwarf. This type of star had long had a bad reputation in the search for life, because yes, many red dwarfs, especially young ones, are prone to violent eruptions or flares. These flares can suddenly increase the star's brightness by 100 times or more. They can release intense ultraviolet and X-ray radiation. This radiation, in theory, could strip away a planet's atmosphere or bombard its surface with lethal levels of radiation for known life forms. So, for years, scientists viewed red dwarf systems as not very promising places for life. But K2-18b shook this perception as well, because K2-18 is not a particularly young or active star. It produces some flares, yes, but they are not as extreme as those seen on the most active red dwarfs. More importantly, K2-18b's thick hydrogen atmosphere provides significant protection against stellar radiation. And that wasn't the biggest surprise. The real surprise was the lifespan of these stars. While our Sun will live for about 10 billion years, the smallest red dwarfs will burn steadily for 10 trillion years. That's 1,000 times longer than the current age of the universe. This meant that K2-18b, if it has an ocean, had almost infinite time for life to emerge. A star that posed a flare risk could also be the most patient cradle for life in the universe. This paradox required us to rewrite all our rules about where and how to search for life. Thus, all these shocking findings came together. A multi-billion-dollar folding telescope operating with impossible precision. A mission operating over 1 million kilometers away, in a cold close to absolute zero. This telescope looks at a planet orbiting a paradoxical star, both dangerous and incredibly patient. And in that planet's atmosphere, it finds gases that chemically should not coexist. It detects a molecule that should be there but is mysteriously missing. And, most importantly, it captures the ghostly, tentative, but persistent signal of dimethyl sulfide, a molecule on Earth produced only by life, and each finding is revolutionary on its own. But as when they all come together, they show that our understanding of the universe is being shaken to its core. But how does this instrument work? How exactly is that impossible precision achieved? How can it measure that tiny, 1 in 10,000th dimming of a star's light from 120 light years away, so clearly? Because the technology at the heart of this telescope, the real secret of that $10 billion engineering marvel, because the technology at the heart of this telescope, the real secret of that $10 billion engineering marvel, is much more than just gold-plated mirrors or a giant sunshield. Let's slow down. Let's lower the tempo and delve into the depths of how this impossible machine works. Because being able to hear the breath of a world 120 light years away was made possible by the convergence of 3 fundamental technological revolutions. The first of these relates not to the telescope itself, but to the nature of the light it observes. Webb doesn't work with the light the human eye can see. It sees in infrared light. This is a type of light invisible to the human eye, but it carries information about heat and chemistry. The reason for this choice is very simple. Because the universe is expanding. The light from distant galaxies and planets gets redshifted due to this expansion by the time it reaches us. That is, its wavelength stretches, turning from visible light into infrared light. Telescopes like Hubble, which look in visible light, cannot see these oldest and most distant objects. But Webb, with its infrared eyes, can look into the deeper secrets of the universe. This is also what allows it to read the chemical fingerprints of exoplanet atmospheres, because in the technique of transit spectroscopy, those tiny absorptions in the starlight filtering through the atmosphere are much more pronounced in the infrared spectrum. Webb's primary mirror is therefore specially designed. Its 18 hexagonal beryllium segments, each about 1.3 meters wide, are coated with a microscopically thin layer of gold. Gold was chosen not for its beauty, but for its physics. Because gold is a much better reflector than silver or aluminum at the specific infrared wavelengths Webb is designed to observe, it reflects about 99% of the light. This means it can collect those tired photons that have traveled more than 700 trillion miles without losing almost any of them. That is why Webb is not just a telescope, it is a time machine and a translator that can read the chemical dictionary of the universe. If Hubble showed us a picture of the universe, Webb tells us its chemistry, but collecting the right light is not enough. You have to break that light down into its components with incredible precision. This is where Webb's scientific instruments come in. The two most important ones for the K218b observations are NIR-SPEC and NIR-ISS. These names stand for Near Infrared Spectrograph and Near Infrared Imager and Slitless Spectrograph. These instruments split the incoming light into its component wavelengths and measure the intensity at each wavelength with extraordinary precision. You can think of it like a prism splitting white light into the colors of the rainbow, but a much more advanced version. When an exoplanet transits its star, these spectrographs can detect the tiny changes in the star's spectrum caused by molecules in the planet's atmosphere, absorbing light at specific wavelengths. Their sensitivity is truly remarkable. NIRSPEC can detect changes in brightness as small as a few parts per million. This is roughly equivalent to noticing how much a lighthouse's beam dims when a moth flies in front of it. The observations of K218b combine data from both instruments and multiple transits to build up enough signal to distinguish the planet's atmospheric features from background noise. Each transit lasts only a few hours, and the atmospheric signal is a tiny fraction of the star's total light. So, multiple transits must be observed and the data carefully combined. The analysis also required subtracting the effects of the telescope's own instruments, the variability of the star, and the motion of the Earth and the telescope through space. That final spectrum, that single graph showing the signatures of methane, carbon dioxide, and possible dimethyl sulfide, represents the combined result of hundreds of hours of observation and analysis. Without these instruments, the golden mirror would be just a beautiful ornament. But, thanks to these spectrographs, that mirror becomes an ear, capable of hearing even the faintest whispers of the universe. And finally, there's one more thing that makes all this data meaningful. Modeling. The raw data Webb collects means nothing on its own. It's just numbers, points on a graph. What turns these points into a story are the atmospheric models that scientists use. This process involves fitting theoretical models to the observed data and determining which combination of molecules best explains the overall absorption pattern. This requires making assumptions about the atmosphere's temperature structure, the pressure at different altitudes, the presence or absence of clouds, and the mixing ratios of various gases. Different assumptions can lead to different results. For methane and carbon dioxide on K218b, the absorption features were strong and well separated from each other, so the detections were robust. But for dimethyl sulfide, the situation was different. The molecule's infrared absorption features were weaker and overlapped with those of methane. Methane also absorbs at the wavelengths where dimethyl sulfide is expected to absorb or sweat, and the dimethyl sulfide signal had to be extracted from underneath the larger methane signal. This is technically possible, but it requires data with a very high signal-to-noise ratio. That is, the observations need to be sensitive enough to distinguish a small bump on top of a larger feature. The current data is good, but it may not be good enough to make this distinction with confidence. Indeed, since the original results were published, several independent research groups have reanalyzed the K218b data and reached different conclusions. Some analyses support the presence of dimethyl sulfide, while others have found that the data can be explained just as well without it. This doesn't mean something is wrong. It's a sign that the measurement is at the very limit of what current instruments can achieve. The signal is right on the edge of detectability, and small differences in analysis methods can push the result one way or the other. So, more observations and better models are the only way to resolve this uncertainty. But this modelling process is also a testament to Webb's power, because it shows us not only what we see, but also what we don't know. It draws the boundaries of science and gives us a roadmap to push beyond them. Because when these precise instruments, these advanced models, and that golden gateway to the infrared universe come together, what emerges is not just an observation, but a dialogue between us and the universe, conducted in the language of photons. But there's an unseen, more complex layer to this dialogue, and that is the process of weeding out the errors and noise within the data. Because the raw data is never clean, and the real magic that turns that data into a discovery. Because the real magic that turns that data into a discovery lies not in the data itself, but in what is removed from the data. Raw data is never clean, it is filled with noise. So, reliably detecting a signal depends on the ability to distinguish that signal from the noise. You can think of it like trying to hear a whisper in a crowded room. With everyone else talking, you need to filter out all the other sounds to catch that single whisper. That is exactly what Webb does. But it does it from millions of kilometers away, with photons that have traveled across trillions of kilometers of empty space. The first step in this filtering process is to understand and remove the noise originating from the star itself. Red dwarfs like K2-18 can have star spots on their surfaces, similar to sunspots. These spots are cooler and dimmer than the rest of the star. As the star rotates, these spots move in and out of our view, causing small fluctuations in the star's total brightness. If these fluctuations are not accounted for, they can be mistaken for absorption signals from a planet's atmosphere. So, scientists carefully map this variability by observing the star for long periods when the planet is not transiting. This creates a baseline of the star's normal behavior. Then, this baseline is subtracted from the data collected during the transit. This is like a sound engineer first recording a section of just the background hiss to remove it from a recording. This process prevents the star's own personality from masking the planet's atmospheric signature. Without it, even strong signals like methane or carbon dioxide in K2-18b's atmosphere could be lost in the star's own noise. Because the signal from the planet's atmosphere is less than 1/10,000th of the star's total brightness. But the variability created by star spots can be much larger than that. That is why this subtraction process is the first and most critical step of the discovery. But the star is not the only source of noise that needs to be removed. The telescope itself is also a source of noise. As Webb moves through space at 1.5 million kilometers per hour, its temperature constantly fluctuates by very small amounts. Even though the sunshield keeps it at -223 degrees Celsius, even at this temperature, there are microscopic thermal expansions and contractions. These tiny movements cause slight changes in the telescope's optical system, affecting the amount of light that falls on the detectors. This is a condition known as systematic error. To eliminate this effect, scientists model the telescope's behavior with incredible precision. They continuously record the instrument's temperature, position, and other engineering data during observations. Then, they use this data to create a model that calculates the expected effect of systematic errors, and they subtract this model from the raw data as well. This is similar to a photographer digitally correcting the distortion caused by a small flaw in their camera's lens, by knowing exactly what that flaw is. Without this correction, weak signals, especially like dimethyl sulfide, could easily be confused with the telescope's own internal creaks. Older telescopes like Hubble could not make such precise corrections, because their stability and thermal control couldn't even come close to Webb's $10 billion design. That is why Webb is not just a larger mirror, but a much smarter machine that can listen to itself and silence its own noise. This is the silence that makes discovery possible. And finally, even after all this noise is removed, there is one last step to verify whether the remaining signal is real. That is statistical analysis. Scientists use statistical tests to calculate how low the probability is that the signal they've detected is just a random fluctuation of noise. This is expressed as a sigma level. For example, a 3 sigma detection means the probability of the signal being random noise is roughly 1 in 370. A 5 sigma detection means this probability drops to 1 in 1.7 million. In particle physics, a 5 sigma standard is usually required to claim a discovery. The methane and carbon dioxide detections on K218b easily surpassed this threshold. But the dimethyl sulfide detection was lower in the range of about 2 to 3 sigma. This means the signal is interesting and worth further investigation, but cannot yet be considered a definitive discovery. This caution is a fundamental part of the scientific process, because science avoids claims of certainty. Instead, it measures the strength of the evidence and honestly expresses the uncertainty. This is what makes the story of K218b so honest and compelling. It is a mystery yet to be solved, and the solution to that mystery lies in more data and better statistics. That is why that ghost whisper is still there, on the edge of the noise, at the limit of uncertainty, waiting to be confirmed. Thus, we have completed this incredible technical process. A system that uses the power of infrared light, breaks it down with incredibly precise spectrographs, cleverly filters out the noise from the star and the telescope itself, and finally, meticulously measures the statistical significance of the remaining signal. Each step is more complex than the last. Each step is more awe-inspiring than the last. But behind all these technical details, all these engineering marvels, lies what is truly exciting. What do these tools allow us to see? For what was all this effort, this technology, this money spent? Because now, it is time to journey deeper into that world. These instruments have shown us that potential cradle of life. We will now set aside the question of how and focus on the question of what, on life itself. Because the possibilities that lie behind that faint dimethyl sulfide signal are so vast as to render all this technology meaningless, and the climax of those possibilities, the moment has come. The technical details are over. We are now moving beyond the numbers, the engineering steer and the cold physics, because now we come to those moments when the James Webb Space Telescope tore through the fabric of the universe, fundamentally rewrote cosmology textbooks, and touched upon humanity's deepest questions, to its greatest discoveries to date. The climax, maximum speed, the place where the heart of the entire story beats. Hold your breath, because now you will witness the most incredible things Webb has found. This is the forefront of science. This is reality itself. The first shock impossible galaxies. They should not have been there. So lutely not. But Webb looked, and there they were, shining in the darkness at the dawn of the universe. Large, bright, and fully formed galaxies. According to the standard model of cosmology, this was impossible, because, according to that model, in the first few 100 million years of the universe, there should have been only small, faint, scattered proto-galaxies. But Webb saw galaxies like JADES-GS-Z 13-0. The light from this galaxy had been travelling to us for 13.4 billion years. This meant it was a photograph of a moment just 320 million years after the Big Bang, only 2% of the universe's current age. But this galaxy wasn't small and faint. It was astonishingly bright, filled with billions of stars, at least 10 times brighter, 10 times more massive than expected. How could this be possible? How had so many stars formed in such a short time? How had dark matter accumulated so quickly to form these massive structures? Scientists were in shock. Their first reaction was, is there an error in the data? Because this meant that all the theories of cosmic evolution they had built for decades were being shaken to their foundations. But there was no error. The observations were repeated. The results were confirmed. The data was correct. What was wrong was our understanding of the universe. In that moment, cosmology textbooks were torn up. Webb hadn't just shown us a new galaxy, it had shown us that the story we told ourselves about the beginning of the universe might be wrong. Yet that is why this finding was not just a discovery, it was a revolution. But this was only the beginning. Because, at the heart of those impossible galaxies, something even more impossible was lurking. Monsters. Massive black holes that had appeared at a time they shouldn't have, at a size they shouldn't have been. When Webb looked at galaxies within the first 500 to 700 million years of the universe, it found supermassive black holes at their centers, with masses billions of times that of the Sun. This was shocking in itself. But the real impossibility was the ratio of these black holes to their galaxies. In the modern universe, in galaxies like the Milky Way, the central supermassive black hole makes up about 0.1% of the galaxy's total mass. This is a norm. But these first monsters Webb found made up 10% or even more of their host galaxy's mass. This was a ratio 100 times larger than the norm. How could this be? There wasn't enough time to grow that large in such a short period. The laws of physics, the standard models of accretion and mergers, did not allow for it. It was like a baby growing into a 100-kilogram adult in just a few months. Something was wrong. Very wrong. This discovery instantly turned all theories of black hole evolution into trash. Scientists were forced to propose new and radical theories about how seed black holes form. Perhaps the first stars collapsed directly into giant black holes. Perhaps a new type of physics we know nothing about was at play, and Webb had shown that the universe created not only giant galaxies, but also the monsters at their hearts, much earlier than we expected. This was proof that the universe's youth was not calm and slow as we thought, but incredibly violent and fast. And then Webb looked at something even more fundamental, the building blocks of life, chemistry itself, and it found them in the most incredible places and times imaginable. Everywhere. Webb detected the presence of complex organic molecules in galaxies more than 12 billion years old, within the first billion years of the universe, specifically polycyclic aromatic hydrocarbons, or PAHs. These molecules are complex ring structures made of carbon and hydrogen. On Earth, they are found in burnt wood smoke, exhaust fumes, and even on grilled meat. But in the universe, they are chemical precursors that play a critical role in the formation of life's building blocks, and Webb found them at the dawn of the universe. This was an incredible discovery. Because it was thought that the formation of these complex molecules required billions of years of stellar life and death cycles, where stars produce heavy elements inside them, die, and scatter these elements into space. But they were there, almost from the very beginning. This was like the essential materials for a house being ready at the construction site before the blueprint was even drawn. This finding fundamentally changed our understanding of the origin of life. The timeline required for life to emerge was suddenly shortened by billions of years. The universe was not a hostile, Hycean, cold, and empty place. On the contrary, it was teeming with the chemical raw materials for life from the very beginning. This raised the idea that the universe might be prone to life, that it wasn't a random probability, but perhaps a fundamental property. Webb was showing us not just stars and galaxies, but also the potential for life hiding in the empty space between those stars. But all these galaxies, all these black holes, all these molecules, they were all preparation for one single great moment, one climax, humanity's most ancient, most profound question: are we alone? And Webb stopped looking at that distant ancient universe to ask this question, and it came home, to our own galactic neighborhood, to that faint red star just 120 light-years from us, K2-18, and to that strange world in its orbit, K2-18b, 8.5 Earth masses, 2.5 Earth radii, a potential ocean world hidden beneath a massive hydrogen atmosphere. And when Webb captured the faint light filtering through that atmosphere, it found something that would overshadow all these cosmological shocks, that 2 to 3 sigma, that faint, that hesitant signal on the edge of the noise, dimethyl sulfide. This was not a physical impossibility, this was a biological impossibility, because on this planet, as far as we know, There is only one thing that produces this molecule in significant quantities: life. In that moment, suddenly, everything changed. This wasn't like measuring the mass of a galaxy billions of light years away. This was the possibility of hearing a breath from 120 light years away. It wasn't finding a fossil, it was detecting the chemical exhaust of a metabolism, a life process. And in that moment, the scientific world fell silent. All those theories about the age of the universe, the models of black hole growth, they all suddenly became of secondary importance. Because this was not a question about the structure of the universe. This was a question about the meaning of the universe. This was a question about our place in this cosmic ocean. This was Webb's greatest, deepest, and most shattering discovery. Impossible galaxies, monster black holes, the building blocks of life scattered everywhere, and now the potential breath of life. What is the picture that emerges when all of this comes together? What does this mean the universe is trying to tell us? Because each of these discoveries seem to point to one great truth. That the universe, because each of those discoveries seem to point to one great truth. That the universe was much faster, much more efficient, and much more ready for life than we ever thought. This was not a random series of shocking findings. This was a pattern, a narrative. It was the moment the universe told us its own story, its fast and violent version, instead of the slow and boring one we had written. So, Webb's greatest discovery was not a single object or a single molecule. The greatest discovery was this new understanding of the very nature of the universe itself, and this new understanding was supported by other shocking discoveries as well. And one of those discoveries took place right outside our own solar system, less in our own neighborhood, the TRAPPIST-1 system, just 40 light years from us. A stone's throw in cosmic terms, this system consists of 7 roughly Earth-sized planets orbiting a very small and cool red dwarf star. Many of these planets orbit within or near the star's habitable zone. This made them prime targets in the search for life. But there was a problem. TRAPPIST-1 was an extremely active star. It was known for powerful bursts of ultraviolet radiation. So, scientists were concerned that the planets, especially those closest to the star, might have already lost their atmospheres. And Webb looked at the planet TRAPPIST-1b, the innermost world of the system, and shockingly, it found nothing there, no atmosphere. It was completely bare. This was not a discovery, it was an autopsy. For the first time in history, Webb measured the thermal emission, its own heat, of an Earth-sized rocky exoplanet. It found the dayside temperature to be about 230 degrees Celsius, 450 Fahrenheit. This proved that heat was not being redistributed by an atmosphere, meaning there was no significant atmosphere. This finding reignited the debates about the habitability of red dwarfs. How could a star on one hand offer trillions of years of potential for life, while on the other, so cruelly strip the atmospheres from its closest children? Though TRAPPIST-1b's nakedness seemed like a disappointment, it was actually incredibly important, because this was the first proof that Webb could detect not only what is present, but also what is absent. It hadn't proven the ghost of an atmosphere, but the absence of one. This was a revolution for comparative planetology. We were no longer just asking, which planets have atmospheres? We were now asking, why do some have them, and others don't? But Webb's autopsies didn't end there. Because another shock came from an even stranger world, LHS 475b, 41 light years away from us, a planet almost exactly the size of Earth, orbiting another red dwarf, 99% Earth's diameter. When Webb looked at this planet, it again searched for an atmospheric signature, but what it found was again a silence. But this was a different kind of silence. The data definitively ruled out that the planet could have a thick methane-dominated atmosphere, like Titan, but it could not rule out the possibility of a thin carbon dioxide atmosphere. This was an incredibly fine distinction. Webb was not saying whether an atmosphere existed, but what kind of atmosphere it could not be. It was like a detective at a crime scene who doesn't know who the killer is, but can say with certainty that they could not have been tall. The temperature of LHS 475b was also measured, about 315 degrees Celsius, 599 Fahrenheit, several hundred degrees hotter than Earth. This meant that if it had a cloudy carbon dioxide atmosphere, the planet could be very similar to Venus. This discovery once again showed how unbelievable Webb's precision is. We were no longer getting just yes or no answers. We were now getting nuanced answers like, maybe, but not in this way. This was a moment that moved the field of exoplanet atmosphere science from crude detections to a process of precise elimination. Every negative result was actually a positive piece of information. We were narrowing down the recipe for habitable planets in the universe by eliminating the ingredients that shouldn't be there. But beyond all these distant worlds, Webb also taught us shocking things about our own home. It looked at the giants in our own solar system, Jupiter and Saturn, and it saw them with a clarity we had never seen before. It resolved the complex eddies and waves inside Jupiter's Great Red Spot, that centuries-old storm, in incredible detail. But the real shock came from Saturn's small, icy moon, Enceladus. The Cassini spacecraft had discovered years ago that Enceladus spews giant plumes of water vapor into space from its south pole. These plumes were thought to come from a global liquid water ocean beneath the moon's icy shell. This made Enceladus one of the most promising candidates for harboring life in our solar system. And Webb looked at these plumes, and what it saw astonished everyone. The plume it saw was 20 times longer than the moon itself, a jet of water vapor about 9,600 kilometers, 6,000 miles long. That's a distance greater than from New York to Los Angeles. Webb calculated that this jet was spewing about 300 liters of water per second. This meant it would take only 2 seconds to fill a garden hose, and a few hours to fill an Olympic swimming pool. This was unlike anything we had ever seen before. This showed that Enceladus's internal ocean was not just existing, but was incredibly active and dynamic. Webb's infrared sensitivity even mapped how this water spread along its orbit, forming a ring around Saturn. This was living proof that even our own solar system is still full of secrets that can surprise us, and these secrets hold fundamental clues about the origin and spread of life. So, all these epic moments, these paradigm shifts, these record-breaking discoveries come together to form one grand picture. Giant galaxies and monster black holes formed impossibly early. The chemical building blocks of life scattered everywhere at the dawn of the universe. Earth-like rocky planets in our own neighborhood with bare or mysterious atmospheres. The giant ocean jets spewed into space by a moon in our own solar system. And at the center of it all, that single, that faint, that hopeful signal, the potential dimethyl sulfide on K2-18b. Each discovery shows that the universe is much faster, more complex, and potentially more full of life than we ever thought. But now it is time to stop and think, time to slow down and breathe amidst these dizzying discoveries. All this data, all these numbers, all these shocks. So what does this mean for us, as humanity? Where do we stand in this new reality? Because the philosophical weight of these discoveries may be far greater than their scientific importance. And the question that lies beneath this weight, because the question that lies beneath this weight is perhaps greater than all these discoveries. Now it is time to stop and think. Time to slow down and breathe amidst these dizzying discoveries. All this data, all these numbers, all these shocks. So what does this mean for us? How do these discoveries change our understanding of our place in the universe? Because as humanity, we are on the very threshold of this new reality. And this reality is filled with deep and unsettling paradoxes. Facing these paradoxes is both painful and incredibly beautiful. The first paradox is about scale, the vast chasm between understanding and reaching. On one hand, with instruments like the James Webb Space Telescope, we have an intelligence that can analyze the chemistry of a galaxy 13.4 billion light-years away, that can count the molecules in the atmosphere of a world 120 light-years distant. We can grasp the deepest secrets of the universe, its most distant corners. Our minds can fit trillions of kilometers into an equation, billions of years into a graph. But, on the other hand, we're physically trapped on this planet, this blue dot. We are fragile, carbon-based beings, averaging 1.7 meters tall. Our bodies are tuned to the gravity of this planet, the pressure of this atmosphere, and the temperate light of this sun. The vast distances of the universe are just numbers to us, because we can never go there. K2-18. and we, that potential cradle of life, will forever remain beyond our reach. Even with our fastest spacecraft, it would take over 2 million years to get there. That is a period longer than all of human history. This is a tragic reality. The tragedy of having the power to understand the universe, but not being able to touch it. We are like children in front of a cosmic storefront. We marvel at everything we see, but we can never break the glass to touch them. This holds a deep sadness, a feeling of loneliness brought by knowledge, but this is exactly where the but comes in. Because yes, we can never go there, but we can bring it here. The photons from those distant worlds, that ancient light, arrive and touch our telescopes at the end of their billion-year journeys, and in that moment, that world becomes a part of us. Its story merges with our story. We may not be able to reach, but we can witness, we can understand, and perhaps that is a much more powerful act than going. Because to understand is to form a deeper bond than to possess. You are at the very center of this paradox. You are a being with a limited body, living on a tiny dot in this vast universe. But you're also a consciousness that can travel that universe with your mind, that can imagine the oceans of K2-18, that can witness the first moments of the universe. Your existence is living proof of this tragic but beautiful truth. You are that miraculous being who understands even if you cannot reach, who feels even if you cannot touch. And this makes you not a passive observer of the universe, but an active participant. The second paradox is about time, the brevity of the moment and the eternity of the moment. On one hand, there is a 13.8 billion-year-old universe, a mind-boggling timescale where red dwarf stars will burn for trillions of years. In this universe, a human lifespan, an average of 80 years, is less than the blink of an eye. On the cosmic calendar, all of human history is just a fraction of a second. We are nothing more than transient waves in this vast ocean of time. We come and we go. Our individual existence is almost unnoticeable in the grand narrative of the universe. This is a disturbing truth that fills one with a sense of nothingness. The realization of how meaningless all our deeds, all our achievements, all our pains seem on this vast timescale places a heavy burden on one's shoulders. Billions of years from now, no trace of us will remain. Our planet itself may not even exist. This is the most tragic aspect of existence, the deep melancholy brought by our transience. But again, that but arrives. Because yes, our time is short. But that moment, that brief moment, is the moment the universe becomes aware of itself. After 13.8 billion years of silence, on this planet, beings like you and me emerged. And we opened our eyes and looked at the universe. We noticed its beauty, its mystery, its vastness. In that moment, the universe became conscious of its own existence for the first time. It saw itself through our eyes. It thought about itself with our minds. So, that brief 80-year life is not a meaningless void, but one of the most meaningful moments in the universe. We are the means by which the universe comes to know and understand itself. And this brief moment is sufficient for this task. You too are a part of this paradox. Your short life is the culmination of the universe's 13.8 billion-year story. Your consciousness is like a candle flame burning in that infinite darkness. It may be short-lived, but for that moment, it illuminates everything around it. You exist for just a moment. But that moment is as valuable as eternity, because that is the moment the universe, thanks to you, becomes aware that it exists. And the third paradox is about loneliness and togetherness, cosmic isolation and deep connection. On one hand, there is the unimaginable void of the universe, millions of light years between galaxies, trillions of kilometers of emptiness between stars. Each civilization, if any exist, is stranded on the island of its own star system. The cruel limit of the speed of light makes meaningful communication almost impossible. Even if there is life on K2-18b, we will never be able to talk to them. We won't be able to listen to their music, learn their philosophies, nor they ours. This is a deep sense of cosmic loneliness, the fact that the universe is like a crowded but silent party, and everyone is there, but no one can talk to each other. This is a tragic isolation, the painful awareness of knowing others exist but being unable to reach them. We are like souls living in parallel universes, unaware of each other's existence. This thought can make one feel helpless. The fear that no matter how much we search, the only voice echoing in the deep silence of the universe will be our own. But that magic word appears once again. But. Because yes, perhaps we will never talk to each other. But. We're all subject to the same laws of physics. We're all made of the same chemical elements. Those polycyclic aromatic hydrocarbons that Webb found existed in a galaxy 12 billion years ago, and they exist in the cells of your body. The methane in K2-18b's atmosphere is also formed in a swamp on Earth. We are made of the same stardust. The language of the universe is not words, but chemistry, and we can speak this language. This is a universal heritage that connects us with invisible threads. We are biologically separate, but chemically one. This is the deepest togetherness in the midst of loneliness. You are a living example of this paradox. You are alone on this planet, inside your own consciousness. No one can ever fully know your thoughts, or fully feel your feelings. But at the same time, every single atom in your body was forged in the heart of a star billions of years ago. You are, quite literally, a child of the stars. You share the same origin with those distant galaxies, with those potential life forms. You are a part of this cosmic web, alone, but never on your own. And this is the deepest solace, perhaps the greatest truth. When this immense scale, this brief time, and this deep sense of loneliness come together, we understand how fragile, but also how precious human existence is. But there is more to discover on this philosophical journey, because these discoveries make us question not only our place in the universe, but also who we are and what we can be. And another paradox lies at the heart of this questioning. And another paradox that lies at the heart of this questioning is the delicate dance between knowledge and ignorance. Because every new discovery by Webb not only increases what we know, but also slaps us in the face with how vast our ignorance is. This is the most fundamental and unsettling contradiction of a knowledge. The more we learn, the better we understand how little we know. And every answer brings with it 10 new questions, and the horizon of knowledge constantly expands as we approach it. This is a journey without an end. The fourth paradox is between certainty and uncertainty. On one hand, Webb provides us with data of a certainty we have never had before. We can measure the amount of methane in a planet's atmosphere with parts per million precision. We can calculate a galaxy's distance with an error margin of a few million years. These are triumphs of human intellect and technology. They are moments when science unravels the secrets of the universe, bringing order to chaos. This data gives us a solid ground, a reliable foundation upon which to build our theories. This is the satisfying, just confidence-inspiring feeling that knowledge brings. We are no longer just speculating, we are now measuring. We now know this is not a tragic fact. On the contrary, it is one of humanity's greatest achievements. After hundreds of thousands of years of ignorance, we have finally begun to decipher the language of the universe. But, on the other hand, the interpretation of this certain data is shrouded in a deep layer of uncertainty. The data from K2-18b can be interpreted as both an ocean world and an oceanless mini-Neptune. That faint dimethyl sulfide signal could be both a biological signature and random noise. Certain numbers lead us to uncertain conclusions. This is the saddest part of science. The fragility of interpretation despite the robustness of the data. The constant state of doubt that comes from never being fully sure of a conclusion. But then that but appears on stage once more. Because this uncertainty is not a weakness, but science's greatest strength. This uncertainty protects us from dogmatism, from blind faith. It forces us to ask more questions, to collect more data, to constantly test our theories. What keeps science alive is not certain answers, but this fertile uncertainty. You experience this paradox in your own life. You act with absolute certainty on some matters. But most of the most important decisions of your life are made in deep uncertainty, and in those moments, you try to find the right path within that uncertainty. Science does exactly that. And this process is not a destination, but a journey. And that journey itself is far more valuable than the answer. The fifth, and perhaps most personal paradox is between importance and insignificance. On one hand, there is the overwhelming sense of insignificance that these discoveries bring. In a 13.8 billion-year-old universe, in a cosmos with hundreds of billions of galaxies, each with hundreds of billions of stars, how small are your personal troubles, anxieties, joys, your rush to get to work in the morning, what you'll have for dinner, an argument you had with a loved one. How trivial all of this seems next to the potential oceans of K2-18b or so, next to the violent birth pangs of the universe's first galaxies. This is a heavy blow to the human ego. We're so used to putting ourselves at the center of our lives that realizing what a small role we play on the grand stage of the universe can be painful. This is an existential vertigo. It's very easy to feel that everything is meaningless. This is one of the most tragic moments of this journey. The deep sense of nothingness felt in the face of greatness. But, and this is perhaps the most important but on the other hand, this very insignificance offers us incredible freedom and perspective. Because, if our individual troubles are so small on a cosmic scale, then we don't have to attach such great meaning to them. This awareness can free us for a moment from the stress and pressure of daily life. It gives us room to breathe, and more importantly, it allows us to see what is truly important. In the face of the universe's greatness, the value of small human connections, a moment of joy, a moment of compassion, a moment of understanding increases tenfold. Because the one thing the universe does not offer us is meaning. We create meaning ourselves. And we find it in these small, insignificant moments. You stand right in the middle of this paradox. Yes, your anxieties may be insignificant on a cosmic scale. But your consciousness that feels those anxieties is one of the rarest and most precious things in this universe. And with that consciousness, you can choose to show compassion to yourself and your loved ones. With that consciousness, you can find meaning in the beauty of a sunset, in the sadness of a piece of music, in the smile of a friend. The greatness of the universe doesn't have to diminish you. On the contrary, it can be a gift to help you appreciate the small and precious things in your life. What do you feel in the face of these discoveries? On one hand, is it a sense of awe, of wonder, and perhaps a little fear in the face of this unimaginable vastness of the universe, this infinite depth of time, and our smallness in this cosmos? Or on the other hand, is it a sense of pride, of hope, and of joy in the face of the power of human intellect and spirit, which can understand this universe, solve its secrets, and create meaning in this vast emptiness? Both are true. To feel both at the same time is part of being human. Because we are beings who swing between these two emotions, made of stardust but able to understand the stars, mortal but able to imagine eternity, alone but connected to each other. This tension, this paradox is our most fundamental characteristic. And every new image, every new piece of data Webb shows us, makes this tension even more apparent. It reminds us both how small we are and how great we can be at the same time. Thus, on this philosophical journey, we have seen these deep paradoxes the universe offers us. The paradoxes of scale, time, loneliness, certainty, and importance. Each one invites us to be both humble and hopeful. They show us that our place in the universe is too complex and layered to be explained with a simple answer. We now know that we are both a speck of dust and the very consciousness of the universe. We now know that we are both transient and living moments that touch eternity. We now know that we are both alone and interconnected by the fabric of the universe. But, beyond all this awareness, there is one more question to be answered. Perhaps the most difficult one. What will we do with this new knowledge? How should this new cosmic perspective shape our lives on Earth, our relationships with each other, and our responsibilities for the future? Because these discoveries are not just about astronomy, they are about us, and the moral and ethical implications of this new knowledge. Because the moral and ethical implications of this new knowledge force us to confront not only the universe, but also ourselves. And now, we descend to the deepest, most intimate layer of this philosophical journey. This new cosmic perspective pushes us to ask fundamental questions about who we are and who we should be. So, now is the time to ask the most important question. What will we do with this knowledge? How should this knowledge transform our daily lives, our values, and our responsibilities as humanity? Because the greatest impact of these discoveries resonates not in the mirrors of the telescope, but in our hearts and minds. The first confrontation is with the paradox between our definitions and our search. On one hand, our search for life on another world is inevitably based on our own known definition of life. All life on Earth shares a common biochemistry: DNA, proteins, lipid membranes. The biological signatures we look for, oxygen, methane, dimethyl sulfide, are products of this familiar biochemistry. Because searching for the familiar is a reasonable starting point. This is the only example of life we have, so we search for what we know, understand, and can detect. This gives our search a structure, a methodology, and but on the other hand, this approach potentially creates a massive blind spot. What if life on another world uses a completely different biochemistry? What if that life produces molecules that we would not recognize as a biosignature? Then, a planet teeming with life might appear chemically lifeless to our instruments. Because we're only looking for what we know to look for. This is a tragic possibility. The possibility of missing the greatest discovery in the universe due to our own limited imagination and definitions. It's like being in a library full of treasure maps, but only being able to read the picture books. This is one of science's greatest fears, the unknown hiding in the shadow of the known. But here, that but offers hope once again. Because worlds like K218b are so important precisely because they challenge these narrow definitions. A Hycean world is nothing like Earth. A hydrogen-rich atmosphere, a deep ocean with potentially no rocky bottom, the faint light of a red dwarf. If there is life there, it is likely that this life has adapted to conditions very different from our own, and that faint dimethyl sulfide signal, if it's real, is both surprising and comforting. Because on one hand, it suggests that at least some chemical pathways might be universal, that different biologies can arrive at similar molecular solutions. This is the possibility of a common cosmic language. You experience this paradox in your own life. You understand the world through your own experiences, your own beliefs, and your own definitions. But sometimes you encounter someone very different from you, a very different culture, or a very different idea, and in that moment, you realize how narrow your own definitions can be. K2-18b is humanity's moment of encountering this other, and this moment invites us to be more humble, more curious, and more open-minded. The second confrontation is the paradox between knowledge itself and the responsibility that comes with it. On one hand, Webb gives us incredible power over the universe. We can read the atmospheres of planets, understand the life cycles of stars, look back to the beginning of the universe. This knowledge is one of our species' greatest achievements. It is a product of our curiosity, our intelligence, and our cooperation. This gives us a sense of control, a feeling of mastery. We think we are solving the secrets of the universe, understanding its rules. This is the satisfying, powerful feeling that knowledge brings, because knowledge is power. But, on the other hand, this knowledge places a heavy responsibility on us that is often overlooked. This planet, Earth, is the only place in the universe known for certain to harbour life, and we are the only species capable of understanding this planet. But, we are also the only species with the power to destroy it. This is our most tragic and most shameful paradox. This rare and precious consciousness, a product of billions of years of evolution, is at risk of destroying its own cradle. While we study the atmosphere of a world 120 light-years away, we are poisoning our own atmosphere. While we search for life in other oceans, we are polluting our own oceans. This is an impossible contradiction. It's like reaching for the stars with our telescopes, while not noticing the ground slipping from under our feet. But that indispensable but appears once more. Because again, this cosmic perspective, this new knowledge, can also be a wake-up call. When we realize how rare and precious life might be in the universe, perhaps we will better appreciate the value of life on our own planet. The faint hope of life on K2-18b can remind us of the vibrancy and fragility of life on our own planet. This is the cosmic mirror effect. When we look outward, we actually see ourselves more clearly. You are a part of this responsibility. You are an inhabitant and a guardian of this planet. Every choice you make, Every step you take affects this fragile balance, and this universal perspective that Webb offers us can remind you that your daily choices are not just personal, but also planetary, and even cosmic in significance. The hope of finding life on another world might give us the will to save our own. And the third confrontation is with the deep relationship between curiosity and patience. On one hand, there is that insatiable curiosity that is a fundamental part of human nature. We want the answers right now. Are we alone? Is there life on K2-18b? We are impatient to learn the answers to these questions as soon as possible. We live in an age of instant gratification. We access information with a click. We expect results instantly. This curiosity is the driving force of science. It is the fire that pushes us to build new telescopes, to develop new theories, to push the boundaries of the unknown. But, on the other hand, the universe has its own timescale, and that timescale does not align with our hasty nature at all. It took 120 years for the light from K2-18b to reach us. The analysis of an observation takes months, even years. Designing and building the next generation of telescopes takes decades. The universe does not give up its secrets easily. It reveals them patiently, slowly, layer by layer. This is the truth that modern humans have the most difficulty accepting. The fact that some answers may not come within our lifetime. This is a tragic impatience. The sadness of desiring the answer but not having the time to wait for it. Because this is perhaps the most peaceful but this slowness is also a gift. Because this process teaches us not only the answers, but also to wait, to think, to let things simmer. Each new piece of data gives us time to reflect on it, to discuss it, and to make sense of it. The fact that the answer doesn't come in an instant, in a headline, increases its value, because it becomes not a product to be consumed hastily, but a wisdom to be accumulated slowly. You search for this balance in your life. On one hand, you want to reach your goals immediately. But you know that the most valuable things are built over time, with patience and effort. The process of scientific discovery is just like that. It is not a sprint, but a marathon that spans generations, and you are a part of this marathon, and you may not see the answer. But the questions you ask, the curiosity you show, is the fuel that keeps this marathon going. And being a part of this process may be far more meaningful than reaching the end. These deep confrontations, these internal inquiries about our definitions, our responsibilities, and our patience are only a part of the philosophical space Webb has opened for us. But these inquiries bring us to another, even more fundamental point, to that most primal emotion that lies beneath all this searching, all this curiosity, and that is hope itself. Because the most primal emotion that lies beneath all this searching, all this curiosity, is hope itself. And that is why we now come to the final philosophical layer of this journey, to that most delicate confrontation with the nature of hope and disappointment. Because one of the deepest lessons Webb has taught us is that these two are inseparable. They are two sides of the same cosmic coin. Every new discovery both opens a door of immense hope and sows the seeds of potential disappointment. Living with this tension is the greatest challenge for modern humans. The fourth confrontation is the inevitable conflict between expectation and reality. On one hand, there is the immense, almost mythological expectation created by the idea of finding life on another world. This discovery is imagined as one single great moment that will change human history, that will fundamentally shake religions, philosophies, and societies. Media headlines, movies, books, they all tell us that this first contact moment will be dramatic, definitive, and transformative. This expectation gives our search a purpose, an excitement. It motivates us, because as for such a great reward, any effort is worthwhile. But, on the other hand, there is the cold and slow reality of science. The dimethyl sulfide signal on K2-18z is a perfect example of how different expectation and reality can be. The discovery did not come with a press conference, with a definitive announcement. It came as a weak, uncertain, statistically borderline signal. This is a tragic disappointment, to be waiting for that great, cinematic moment, only to be left with a whisper that even experts cannot agree on, a whisper lost in the noise. This is the moment our expectations are shattered by the complex and nuanced reality of the universe. This shows how unsatisfying the nature of science can often be. But, and this but invites us to maturity. But perhaps the real discovery is hidden not in those big moments, but in these small, less uncertain steps. Perhaps the beauty of science lies not in giving definitive answers, but in leading us to ask better questions. What K218b has taught us is that discovery is not a destination, but a process. And this process is far richer, far more honest, and far more human than that grand expectation. You have experienced this conflict many times in your life. A job, a relationship, a project you started with great hopes. Sometimes it doesn't turn out as you expected. Reality may not resemble that bright version of your dreams at all. And in those moments, you are disappointed. But then, you realize what that process has taught you, the experience you gained along the way. And you understand that what was truly valuable was not the destination, but the journey itself. The search for life is exactly like that. And this offers a much deeper satisfaction. The fifth confrontation is with the difference between individual and collective consciousness. On one hand, these discoveries find an individual echo in each of our minds. You filter this information through your own personal lens of experience. You interpret it with your own worldview, your own beliefs, your own fears and hopes. This is a highly personal, almost solitary experience. Feeling your own smallness in the face of the universe's vastness, realizing your own transience in the face of the depth of time. These are profound moments that take place within your individual consciousness. This is the tragic loneliness of existence. The fact that we cannot fully share even our deepest experiences with others. We each live alone in the universe of our own mind. But, on the other hand, these discoveries are also the product of one of the greatest collective projects in human history. The James Webb Space Telescope is not the work of a single person, a single country. It is the result of the collaborative work of tens of thousands of scientists, engineers, technicians, over decades, across generations. People who speak different languages, come from different cultures, have different beliefs, came together for one common purpose: to understand the universe. This is the brightest triumph of humanity's collective intelligence and spirit of cooperation. This is the most beautiful truth. That no matter how divided we may be as individuals, we have the ability to come together when we face the biggest questions. You are a part of this collective consciousness. You stand on the shoulders of Newton, Galileo, Einstein, and thousands of scientists whose names you've never heard. The knowledge they accumulated allows you to watch and understand this documentary. And your curiosity, your interest in this subject, helps this collective project to continue. You may be alone in your individual consciousness. But, in this great intellectual adventure of humanity, you're a member of that giant family, and this, even in the moment of deepest loneliness, can give you a sense of belonging and purpose. As we approach the end of this long and deep journey, how do you feel? Perhaps a little tired in the face of this dizzying complexity and vastness of the universe. Perhaps a little uneasy in the face of all these paradoxes, these unsolved questions, and these uncertainties. Or perhaps you're filled with a sense of gratitude and tranquility in the face of this triumph of human intellect and these generous secrets of the universe. Whatever you feel, it is all valid. Because this journey was not about finding simple answers. This journey was about asking deeper questions, gaining a broader perspective, and learning to listen to the silent music of the universe. And this music is sometimes sad, sometimes joyful, but always profoundly meaningful. We now know that our place in the universe is too complex to fit into a simple definition. We are both insignificant and priceless. We are both alone and interconnected with everything. We are both ignorant and wise enough to solve the secrets of the universe. This new knowledge invites us to be both humble and to dream big. This journey has taken us from one end of the universe to the other, from the beginning of time to the present day, from the golden mirror of a telescope to the depths of our own hearts. Now, it is time to stand amidst these dizzying discoveries, take one last breath, and bring all that we have learned together. Because when all these pieces come together, the resulting picture whispers a fundamental truth, not only about the universe, but also about what it means to be human. And that whisper is perhaps the most precious treasure of this entire journey. With Webb, we witnessed the farthest corners of the universe and the chemistry of life. But there's a chilling possibility I haven't told you. What if this immense order we see is just a line of code? Pixels, error codes, and processor limits. Perhaps reality is just an illusion. On our next journey, we will question whether the universe is a simulation. Are you ready to pull the plug? Came as a weak, uncertain, statistically borderline signal. This is a tragic disappointment. To be waiting for that great cinematic moment, only to be left with a whisper that even experts cannot agree on, a whisper lost in the noise. This is the moment our expectations are shattered by the complex and nuanced reality of the universe. This shows how unsatisfying the nature of science can often be. But, and this but invites us to maturity. But perhaps the real discovery is hidden not in those big moments, but in these small, less uncertain steps. Perhaps the beauty of science lies not in giving definitive answers, but in leading us to ask better questions. What K218b has taught us is that discovery is not a destination, but a process, and this process is far richer, far more honest, and far more human than that grand expectation. You have experienced this conflict many times in your life. A job, a relationship, a project you started with great hopes. Sometimes it doesn't turn out as you expected. Reality may not resemble that bright version of your dreams at all. And in those moments, you are disappointed. But then, you realize what that process has taught you, the experience you gained along the way. And you understand that what was truly valuable was not the destination, but the journey itself. The search for life is exactly like that. And this offers a much deeper satisfaction. The fifth confrontation is with the difference between individual and collective consciousness. On one hand, these discoveries find an individual echo in each of our minds. You filter this information through your own personal lens of experience. You interpret it with your own worldview, your own beliefs, your own fears and hopes. This is a highly personal, almost solitary experience. Feeling your own smallness in the face of the universe's vastness, realizing your own transience in the face of the depth of time. These are profound moments that take place within your individual consciousness. This is the tragic loneliness of existence. The fact that we cannot fully share even our deepest experiences with others. We each live alone in the universe of our own mind. But, on the other hand, these discoveries are also the products of one of the greatest collective projects in human history. The James Webb Space Telescope is not the work of a single person, a single country. It is the result of the collaborative work of tens of thousands of scientists, engineers, technicians, over decades, across generations. People who speak different languages, come from different cultures, have different beliefs, came together for one common purpose: to understand the universe. This is the brightest triumph of humanity's collective intelligence and spirit of cooperation. This is the most beautiful truth. That no matter how divided we may be as individuals, we have the ability to come together when we face the biggest questions. You are a part of this collective consciousness. You stand on the shoulders of Newton, Galileo, Einstein, and thousands of scientists whose names you've never heard. The knowledge they accumulated allows you to watch and understand this documentary. And your curiosity, your interest in this subject, helps this collective project to continue. You may be alone in your individual consciousness. But, in this great intellectual adventure of humanity, you're a member of that giant family, and this, even in the moment of deepest loneliness, can give you a sense of belonging and purpose. As we approach the end of this long and deep journey, how do you feel? Perhaps a little tired in the face of this dizzying complexity and vastness of the universe. Perhaps a little uneasy in the face of all these paradoxes, these unsolved questions, and these uncertainties. Or perhaps you're filled with a sense of gratitude and tranquility in the face of this triumph of human intellect and these generous secrets of the universe. Whatever you feel, it is all valid. Because this journey was not about finding simple answers. This journey was about asking deeper questions, gaining a broader perspective, and learning to listen to the silent music of the universe. And this music is sometimes sad, sometimes joyful, but always profoundly meaningful. We now know that our place in the universe is too complex to fit into a simple definition. We are both insignificant and priceless. We are both alone and interconnected with everything. We are both ignorant and wise enough to solve the secrets of the universe. This new knowledge invites us to be both humble and to dream big. This journey has taken us from one end of the universe to the other, from the beginning of time to the present day, from the golden mirror of a telescope to the depths of our own hearts. Now, it is time to stand amidst these dizzying discoveries, take one last breath, and bring all that we have learned together. Because when all these pieces come together, the resulting picture whispers a fundamental truth, not only about the universe, but also about what it means to be human. And that whisper is perhaps the most precious treasure of this entire journey. With Webb, we witnessed the farthest corners of the universe and the chemistry of life. But there's a chilling possibility I haven't told you. What if this immense order we see is just a line of code? Pixels, error codes, and processor limits. Perhaps reality is just an illusion. On our next journey, we will question whether the universe is a simulation. Are you ready to pull the plug?